Today we studied ESA26H, a second look at the harmonic oscillator. Until now, we have shown that the physical path of a free particle with mass m departing from point A at time ta and arriving at B at time tb, a free particle, so this following a straight line, to satisfy the condition that the time integral of the Lagrangian integrated over the interval ta tb becomes minimum for a free particle, and if it is a harmonic oscillator, for example, we will find what happens. So it was the minimum. It was the minimum in the case of a free particle. In the Lagrangian for a free particle is defined by the kinetic energy, that is 1/2 mass times velocity squared. We'd like to investigate the variation from the condition that we have found for a free particle to a more general case that satisfies the Newton's law of motion that has non-vanishing force. Newton's second law of motion is F equals ma. The net external force is the product of the mass and the acceleration of the particle of that mass. To simplify our analysis, we restrict ourselves to a simplest case whose solution is exactly known already. So we would like to consider a simple harmonic oscillator that has the net force that is the restoring force of a spring. Mass m is attached to a spring whose spring constant is k, and displacement from the equilibrium position is denoted by the vector x. Then the force applied to the mass is minus k times displacement x. By substituting mass times acceleration for the net force, we arrive at the equation of motion. Because this equation of motion is satisfied in any case, we can construct a little bit complicated equation of the identity. Whatever vector you may bring in, you can take the scalar product to find the right-hand side to be 0. Why? A 0 vector scalar product with some constant is 0, because the magnitude of 0 vector is 0. Just like that, whatever x you may bring in, as long as x is satisfied by the equation of motion, the scalar product with the arbitrary vector, this delta x is arbitrary vector at the moment. Scalar product with this left-hand side of the equation of motion vanishes always. By the way, we'd like to replace this arbitrary vector with a little bit specific vector that satisfies the boundary condition. That means its value is 0 at endpoints. Endpoints means starting point at time ta and endpoint at time tb. That means if this is a path that is a physical means that satisfies the equation of motion. If we deviate, this is x of t. If we deviate this one by a little amount, this is a delta x of t. While we vary, we allow the variation from the physical path to the fictitious path in the middle. We do not allow the shift from the physical endpoint. Therefore, we have a constraint. So, because this equation is satisfied, whatever vector you may bring in, it's fine if it is still satisfied, even if we introduce an additional condition that the endpoint doesn't, and the value of this arbitrary vector is 0 at endpoints. Next, we apply Leibniz's derivative rule, that is, derivative of a product is a prime b plus ab prime. We use a similar relation. This differential, it is very similar to our differential, that is the variation from the physical path. All right, we'd like to compute this one that appears as the first term. This one may come from the derivative of a b, that is the time derivative of a b and a time derivative of b. We just replace this one with the scalar product of two vectors. Scalar product of two vectors, and replace a with mx dot and b to be delta x vector. Then we just move this one, move this second term to the left, or the first term to the left. Then we find the identity. Now we substitute equation of motion for the harmonic oscillator. The force is m mass times acceleration. That force is minus kx, so we substitute minus kx for mx double dot. Then, rearranging this equation of motion, this identity, we arrive at the equation of motion. Where is the equation of motion? This is nothing but the identity, and we substitute this mx minus kx for mx double dot. Now, we would like to integrate this equation over the interval. By the way, this is a total time derivative. Therefore, the integral over the interval becomes very simple. Why? Integrand evaluated at endpoints at TB and TA and difference. By the way, we have a constraint that the variation from the physical path to an arbitrary path is 0 at both endpoints. As a result, this is 0, this is 0. So this will remove this complicated total derivative term in the equation. After that, we are left with the contribution of the second and third term. Because we have integrated over t, the result is that. By the way, we are familiar with the Leibniz rule. The 1/2 x squared, the differential is x dot dx. Similarly, we have a variation of the path that may bring the variation of the 1/2 x dot squared. Similarly, by replacing the differential operator d with the delta, now this one can be replaced with the left-hand side, and this guy can be replaced with the left-hand side. Substituting these values for these and these, we arrive at the point. We began with the equation of motion for the harmonic oscillator, and we arrived at this integral equation. But as soon as we apply Leibniz rule for the derivative generalized to the variation, we arrive at the variation of 1/2 mass times velocity squares minus 1/2 spring constant x squared. All right, what's that? The variation of this time integral over the interval whose integrand is kinetic energy subtracted by the potential energy. That variation is 0. All right. So equation of motion that can be obtained by Newton's second law is equivalent to the fact the variation of the time integral whose integrand is kinetic energy subtracted by potential energy. And that is 0. All right. So now we are ready to define the action. We call it action S of a mechanical system. Action S is defined by the time integral of the Lagrangian. And this integrand called Lagrangian is defined by the kinetic energy of the particle subtracted by the potential energy of that particle under a certain conservative force. What we have right now for a harmonic oscillator is minus kx, that is the force, and the corresponding potential energy is 1/2 kx squared. All right, we have shown that the equation of motion is equivalent to the fact that variation of this system, the action, variation of action is 0, is equivalent to this. That means this equation of motion gives the solution called the physical path, and the physical path is the path at which the action of the corresponding system, that is the time integral of the kinetic energy subtracted by the potential energy, has an extremum. Why extremum? because the first order derivative vanishes. What we are interested in is whether this extremum is either the maximum or the minimum. If it is the case, minimum. If it is the case, maximum. Their first order derivative is 0 at this point, but second order derivative is a positive because the slope keep increasing, slope keep decreasing. So delta x at order delta square is a positive in this case, and order delta squared, it is a negative. It is a negative, and this is positive. And at order delta, variation delta, the action has an extremum. This is maximum, minimum. We do not know whether it is a minimum or maximum. All right, let's go ahead. Again, we define the action of a mechanical system is the time integral from the starting point to end point. Starting time to end time, this time integral has the integrand called the Lagrangian that is defined by the kinetic energy subtracted by the potential energy. The shape of the potential energy may vary depending on the system, and right now we are interested in the harmonic oscillator, whose solutions are completely known. Now we extend our variation to order delta squared. The previous derivation, we kept only the order delta contribution. Now we extend it to order delta x squared. Let's see what's the variation of the integrand. Integrand is Lagrangian. Lagrangian is kinetic energy. What is subtracted by potential energy? But a variation of the kinetic energy can be computed by substituting x dot plus delta x dot for the original x dot. So this difference may bring in the difference, the variation due to the variation of the kinetic energy due to the variation of the path from x to x plus delta x. Sure, this is a vector. Similarly, the potential energy, 1/2 kx squared, can be varied by replacing x with x plus delta x. So, this is the variation of the potential energy. This is the variation of the kinetic energy. And then we have to integrate this variation of the integrand during the time interval from TA to TB. We still keep the restriction. Why? Because this derivation of the equation of motion, extension of the equation of motion, require this endpoint constraint to remove the total time derivative explicitly. All right. Therefore, we arrive at the point we have canceled the leading contribution x dot squared and then expansion of a plus b style. That's that 2ab plus b squared. 2ab plus b squared. Similarly, the variation of the potential energy is 2ab a plus b squared subtracted by a squared, 2ab plus b squared. All right, we substitute this integrand for the variation of the action. right? So mass x dot delta x dot 1/2 delta x dot squared, and similarly x dot delta x plus 1/2 delta x squared. We are familiar with the first contribution of order delta, and we combined order delta x squared contribution separately. We remember from the physical path, the leading contribution that is order delta vanishes. Order delta contribution vanishes. Order delta contribution vanishes. Order delta contribution vanishes. Therefore, we can remove the first contribution explicitly. Now we are ready to attack the second order contribution in delta. So 1/2. Wait a second. 1/2 delta x dot square, subtract m mass, and k spring constant delta x squared. All right. Now Leibniz rule can be used to express, because delta x dot is a delta dt dx, and the time derivative of delta x. Okay, this one is defined by this. Therefore, I keep the delta x dot a single delta x, and I rewrite the a single another delta x dot by this time derivative of delta x. Then, again, Leibniz rule can be used to find the derivative of these product, and subtract what? Additional term. That is unnecessary term is a double time derivative of delta x dot delta x. All right. As a result, this contribution has been replaced with this, and then mass times double derivative delta x, and we have negative sign because of this. Next, we have minus k delta x squared. That is explicitly delta x squared. We don't have to modify it anymore. And if we bring in here, because this both of them has a negative sign, we have factored this negative sign out. By the way, we again find this is a total time derivative. Total time derivative can be evaluated very simple. And the integrand is this. We have a delta x that appears at both endpoints. So this one we do not need, and this one vanishes. The only contribution that survives in the order delta squared contribution is this term. And we find 1/2 minus 1/2 mass, and this one is copied here, and we know k over m square root is omega 0, so omega 0 squared is k over m. So square of the characteristic frequency of the simple harmonic oscillator is given in here. Finally, our final result shows that this is the variation of the equation, not equation, the variation of the action evaluated to order delta square is greatly simplified in this form. Okay. We still do not know whether this is a zero or positive or negative yet. Why don't we bring in the physical solution? Physical solution. This is the physical solution for the x. And why don't we introduce a variation from the physical path? The variation of the physical path must satisfy that the variation evaluated at TA and variation evaluated at TB must be 0. We can make a trick. We know sine 0 equals 0 and sine pi equals 0. So we can manipulate the coefficient of time so that it appears that t minus the ta equals 0 at t equals the ta and tb minus ta equals 0 at t minus ta equals pi at t equals the tb. That can be done by choosing the argument of sine to be this, where n is a positive integer. Now we substitute this variation delta x to this definite integral explicitly. The substitution is possible. Delta x squared is nothing but the square of this. And what about delta x dot squared that has cosine dependence? And the frequency, angular frequency squared, is pulled out due to the time derivative. We shall find this delta x s evaluated to order delta squared depends. The sign depends on the condition. Let's see. Delta s, and we substitute these values for delta x squared and delta x dot squared as it is. The evaluation of sine squared and cosine squared is nothing but the 1/2. Sine squared, cosine squared, that's evaluation. 1/2 times it's a period to pi. But the period is the interval is pi instead of 2 pi. So this one is to be multiplied to evaluate the integral. Finally, that appears as a front factor. So this one becomes half of pi multiplied 1/2, and this one half of pi multiplied 1/2. So they are the same actually. Finally, we find these conditions are satisfied. If n is this amount is smaller than k over m, this is negative. And if n is large enough, because k over m is fixed, that is omega 0 squared is fixed. If n is greater than a certain value, it becomes a positive. So we don't know to order delta s, to order delta squared, we do not know whether the action is minimum or maximum. So the least action principle is true only if the particle is a free particle. That's it for today. Thank you.